caption you want. When I originally saw it, that wasn't the caption, but I figured, yes. You do have to be careful when you get some nerds or science teachers out on the playing with kids. Now, did anybody see, there was a commercial I should have reviewed, but I remember seeing it on YouTube, and they hung people upside down. So they were hanging like the balls in the Newton's cradle. And they did. They lifted one up with a wire and a machine, and then they let go of him, and he ran into his buddies, and they knocked each other. Yeah, and that's what I was thinking. What the heck's going on here? There's lots of problems with this. Well, then they had them all wear, they were wearing helmets, by the way. But then they had them switch and wore a different helmet. And that's who the company was, the commercial was for. So they did it again, and it worked better. The idea being their helmets were superior. They would protect you more. I mean, the whole thing was kind of bogus, but it proved their point for their commercial, and I just thought it was funny they were using a Newton's cradle with live human beings, but still. So yeah, be careful, I guess. Merry-go-rounds are another one I like to have fun on. We'll come back to that. I chose not to cover centripetal force, moments of inertia. It's like rotational inertia. You know what inertia is now, resistance to change its motion? Well, it works if you're going in a circle too. Things that are already moving in a circle want to keep going in a circle. But you can change how the mass is distributed and change the rotational inertia. Just like something with more mass will have more inertia. Something where the mass is farther away from the axis of rotation, like an ice skater putting their arms out, will have more rotational inertia versus when they come in. And you can change the speed that they spin at. On a merry-go-round, it's fun. If you all are on the outside and you get it spinning up, you're going so fast, you have a certain rotational inertia. And then while it's moving, if they all try to walk in sync towards the middle, it's like the ice skater bringing in their arms and legs. And the merry-go-round just starts going faster and faster. And if they're not hanging on, you know, there could be trouble. But it's kind of fun. You know, that reminded me of that with the playground physics. All right, before I continue with energy, do you have any questions? Yes, Laura. Which was my part in the quartet? Thank you for asking. Any but tenor. We were called the permutations. Anybody like math in here? We all, when we got together, were basses. And so about every other song we sang, we were singing different parts because, well, I want this one, I want this one. There was one guy that just couldn't sing that low, so he generally took the tenor. He sounded better than me anyway. So actually, I never got to sing bass because there was one guy that could only sing low, well, you know, relatively speaking. So I was usually lead or baritone. All right, let's see. We got work to do. No, just kidding. Work is force times distance. Now, I want to specify up front, this is one that can confuse some physics students. Because in physics, work is a little different than work in the real, I don't want to say the real world, but you know, for common people. the layman's term. I'm putting my foot in my mouth. But you know what I mean. Most people's definition of work is a little different than scientists' definition of work. They're the weirdos, right? So let me specify. We got this equation. And normally we say we're doing work, we're exerting energy, we're pushing or something. But if I come over here and push on this door, you have to remember that I unlocked it, and so I forgot about that. Let's push on the wall. All right. You push on the wall. Am I doing work on the wall? What do you think? Oh, we got yeses and nos. More yeses I'm seeing. Oh, a no. We get more no's than normal. Non-scientists would almost always say yes. That's people's gut. I'm exerting a force on the wall, absolutely. Is it having any effect on the wall? No. in physics, we say I am not doing any work on the wall because I'm not transferring any energy to it. I'm not causing its kinetic energy to change. It's not moving. I'm not changing its position, its location. I'm not storing any energy in the wall just by pushing. So yes, I exert a force, but it doesn't make it move. So in physics, work is only done on something if it makes it move. And that's what I wanted to specify. Yes, Patricia?
That's where I get mixed up with the gravity ball and the sticky little ball that hits it and it's supposed to move something or other.
Oh, and the homework? The bowling ball and the little ball that sticks to it?
Yeah, because it didn't really do anything, but it was supposed to exert the same amount of...
Yeah, if I remember too, there was like a bowling ball and a little sticky ball. And so it's like, this one was at rest, I believe. So its momentum is 0, and this has some momentum of whatever its speed is. So the total momentum is just mv plus 0. After the collision, there must be total momentum be the same, but they're stuck together now. You got the ball on the... it's stuck to it. So now you have a combined mass, a big M plus little m, moving together at some final velocity. That has to equal what it was initially. So it does have combined momentum now. So it is moving a little bit. And I think you guys answered from the air track. What's your gut say? Will the bowling ball be moving which direction? Point. Right. But not very fast, right? This was moving that way initially. Will it have sped up or slowed down? Slowed down. So it won't be moving as fast because the bowling ball slowed it down. So this transferred some of its momentum into the bowling ball. So it now has a little momentum itself, and it has less momentum, but the combined total momentum is what this one started with. So yeah, it should stick, and they should move very little this way with some combined momentum. Does that help?
How do you know the door's not moving a teeny bit?
Technically, yeah, I have a demo for that actually. I can rig up with an optical lever. If you have a sensitive enough instrument, yeah, when I push on this, it actually does flex. We never notice it, but it does, very, very small. And so, yes, technically, I do a little bit of work on it. Yeah. For my argument, I was just pretending like it's not moving. So my point is, something doesn't move, we haven't done work on it in science. So it's interesting too. It's path dependent. I can exert work against gravity on the floor to move myself. Now I just exerted work to get up here. It's now stored in what type of energy? Potential energy, right. Gravitational potential energy. Good. But if I walk back down, doing work again, I get back here to the exact same spot. If I look at the whole journey, in physics, we would say, I've done no work because I started and stopped, ended up in the exact same spot. So that one can be counterintuitive because energy was exerted. Energy was lost in doing that. But we would say, ultimately, I've done no work on me if the beginning and ending position are exactly the same. I intend to get the simple machines at the end, but the one I like using is an incline. An incline plane is one of the simple machines. And how many of you have been asked to help move your friends, or you had to move, and you're loading in the truck, and you got the big piano or refrigerator or washing machine, and you can heft it up onto the back of the truck. You can exert work on it, make kinetic energy, potential energy. You can do that. You'll apply a force for this distance. By the way, the distance is in the same direction the force is applied. Because you can push on something and make it move kind of diagonal. So the perpendicular direction, not the perpendicular. The parallel one is what you want. Example, well, I can use this example, and then I'll come back. I'm exerting a force vertically to lift myself, to move, and so I would look at the vertical distance to determine how much work has been done when I get up here. Think about it. Gravitational potential energy is based on my height, and that's the energy I have now. If energy is conserved, then the amount of gravitational potential energy I have now was equal to the work I put into the system here. Whoop. Gravitational potential energy was mg, our weight, times the height. So in that case, the distance I moved, the work I did was the force vertically to lift myself that height. So in that case, these would be the same distance. Like this. But along comes an inclined plane, and most of us like to use a ramp. So you can start down here and push it up the ramp, right, and get it to the same height. It ends up with the same amount of gravitational potential energy, correct? So I put the exact same amount of work I exerted the same amount of work on the block, whether I go this way or whether I go this way. Which one went a longer distance? The ramp. So in that case, I do the exact same amount of work either way. But one of them travels a bigger distance and one of them a smaller distance. So what happens to the corresponding forces needed? Very good. The longer distance requires less force. Vertically lifting, right? This one will require more. And you knew this because lifting that refrigerator straight up is a lot harder than pushing it up the ramp, right? And by harder, we mean force. So if you can't lift it, because you can't overcome its weight, you can use an inclined plane, a ramp. And you still have to exert force, but less force. I can do this one. I just have to do it for a longer distance. So the energy put in is the same, but the forces are different. That's what simple machines do. They're not magical things that can multiply energy. Energy is conserved. Total energy is always conserved. But you can affect the distance or the force needed. That's what simple machines do. Sorry. We'll come back to simple machines some more. And then we have this, kinetic energy. Energy associated with motion. And I ended with power, a P, and that's energy per time. I like writing it generically because we'll see this again in electricity and other things. It's always the rate at which energy is being used, energy per time. In this case, we can look at the work we did per time. So there's two ways to change power. You can do more work in the same amount of time. This would be bigger. That would be more power. Just do more work in the same amount of time. Or you can do the same work in less time. Do it more quickly, like me running up the steps. That would be more power. Again, I get to the same height, so I'm putting in the same amount of energy, but I did it faster. And so you knew something was different, and that's power. That would require more power. The units of these, energy, all of these, are measured in joules, which is just a big J. It's a guy's last name. It was named after him. You can see that in this one, force was measured in what? Newtons, and distance in meters. So a Newton meter is the same thing as a joule. If we look at this one, mass is in kilograms. Gravity, acceleration is in meters per second, and height is in meters. So you could write all that out. Kilogram, meter per second squared times another meter. So it's really meter squared over second squared. That's a joule. It's consistent. Because force, this is a force, right? It's weight. That's in newtons. Newton meter. And then it works with kinetic energy too. You have a kilogram times a meter per second squared. So it's meter squared, second squared, like we had up here. That's a newton. I mean a joule. So energy is measured in joules. Well, it kind of depends on how you're looking at it. And if you forget, you can always write them out. So for work, which is in joules, it was force, which was in newtons, and distance, which is in meters. So a newton meter. If you were looking at the other one, it was kilogram per meters per second squared times another meter. So that's meters squared over second squared. That's also a joule, because this is a newton. It's a force. And then same game with kinetic energy. Another unit you guys might be familiar with are calories. Those of you that diet, watching your diet. Calories is a unit of energy, like joules. You could convert to get between the two. It's chemical energy that's stored. So for power, we have a joule per second, which is a watt. A what? A watt. What? Watt. Now, where have you heard watts before? What do you usually hear? Where do you hear watts? Electricity. It was speakers or light bulbs. They'll say right on it the wattage. Now, that's the power. That's the rate they're using energy. It can use a lot of energy at a certain amount of time, or it can use the same amount of energy but more quickly. That's telling you the rate you're using energy. Okay. Who likes to go to Lagoon? La Lagoon, an amusement park rides. Say again? I don't know if they finished the new ride. I haven't been following. Those of you that like to go to the amusement parks, do you know why most people like amusement park rides? What is it about the rides you like? Those that like it. Why? The rush. But what? What gives you the rush? Have you ever thought about it? What makes it so exciting? Not sure. Most people don't think about it. When I usually get answers, I won't wait as long. A lot of people will say speed. They like going fast, or the heights also. It's actually not the speed that people like. It's changing speed. Because your inertia says if you're going a certain speed, you'll stay at that speed. It's like an airplane. You're cruising. You're going fast in an airplane, but most of the time you don't notice it until you hit turbulence. And that's when it tries to change your velocity. Acceleration is why people, unbeknownst to them, usually like roller coasters and rides. It's that change in direction or speeding up or slowing down. The woo, the whoa. That's what they either like or don't like. Well, there's my little loop-de-loop. You can think of it as a roller coaster ride. If we need to clear here, we need to make it around here without falling off, scientists will calculate how fast it needs to be going there. The kinetic energy then, if it's got speed, it'll have kinetic energy. There's a minimum amount needed to make this. They'll set it equal to centripetal force, which we didn't study. They'll balance it, and you know how fast it's going. So I know how much kinetic energy we need to clear this. So they work backwards. How high do I need to start so that we have enough energy in the first place to meet that condition. You now are smart enough to do this. You can design roller coasters. Work it out with me. What types of energy will it have here? I already gave you one. Kinetic energy. But it will also have potential. Right. So at this point, let's draw a picture, because you know I like pictures. All right, that was too big. So at point A here, we have kinetic energy and gravitational potential energy. It's moving and it's at a certain height. You could figure that out if you knew how high up it was, right? And if you knew how fast it was going, the velocity at this point, and its mass. It'll be on the inside, and its mass. Well, here's the clincher. Conservation of energy. That's the total energy it has there. So you have to start with that much total energy over here. When you start, what's your kinetic energy? Right, you're not moving. What's your gravitational potential energy? Well, that has to equal the total. So let's call this point B. So the energy at A has to equal the energy at B. So the energy at A is 1/2 mv squared plus mgh. This h, we'll call it HA. And that's got to equal mgh at B. How high up you start over here? Are you with me? So you could just plug it in and figure out how high up you need to start. That's where all the energy comes from in roller coasters. They do work to get it up there. They either shoot you up, or you know that, and you finally get there. They put energy in the system as gravitational potential, and it's enough to finish the entire run. They do a little more, because where's some of that energy going to go, we know. I heard mumbling, but I made none of it out. Friction and sound. Sound's a form of energy, and friction will create heat. Friction is a force. It does work on the cart and creates heat. Yeah, those will escape our system. And so we'll need to start with a little more so that we still have enough kinetic energy to clear here. Fortunately, they have safety things, you know. You won't ever fall off of there even if you stop. But so if we start at the same height, we now have the same gravitational potential here as we do here. But wait, we need kinetic energy here also. So I know we need more. Let's go up a little higher. Oh, that would have been an exciting ride. A little higher. There we go. I heard it actually come off the track there. Let's go slightly higher. There we go. But you know the total energy, you can figure out how fast you're going anywhere. If you know what you start with, that's equal to what it is here. Kinetic plus potential, kinetic plus potential, kinetic plus potential. There's a little less potential here, so it'll probably be going faster than it was here. You know, and it's that game. Conservation of energy. All right. This is some ball chain I bought at the hardware store. It's like that stuff, you know, when you turn off lights or your ceiling fan or something. There's nothing special about it. I put it in a cup. It's all connected. And you guys know what happens now. I'm going to let it fall over the edge. Where will it go? Down, because we know things fall. They accelerate. So, ready? Ooh, that about hit me in the face. What did you observe? Yeah, it goes up. It starts going up before it falls until it gets caught, and then it knocks it down. But then it starts going up again before it falls. Why? Any thoughts? What do you think?
It has to do something with gravity?
It does have something to do with gravity because it's pulling on it. It's pulling it down. But that would make the chain go down, so something else is going on in addition to that. There does send waves. It can ricochet back up through, and that's why you see the warping. Good, that adds to it, but that doesn't add a force to make it go up. There we go. Something to do with potential and kinetic energy balancing. Absolutely. Let's go with that one a little bit. As it falls, up here it has gravitational potential energy. As it falls, that's converted into kinetic energy as it goes faster and faster and faster and loses potential energy. So if you just take the end, it falls, it goes faster, faster, and faster and faster. But the chain's connected. And so the chain in here kind of pulls on it. That can only go so fast. At some point, it doesn't go any faster because this chain's holding it back. But it's still falling. How can something still be falling and not changing kinetic energy? We've done an example in this class, talked about it several times before now. When things were falling. Very good. Terminal velocity. It's like a terminal velocity. In this case, you got its weight pulling it down, and instead of air resistance holding it up, we got the chain tugging on it. And at some point they balance, and it doesn't go any faster, so it doesn't gain any more kinetic energy. Does that make sense? If it doesn't speed up, you don't increase kinetic energy. Well, where does that energy go then? Because it's losing potential energy. Whoop! It causes it to raise up over here. Does that make sense? So it's falling, but it's not going into kinetic energy. It goes into potential up here. Is one way to think of this. Now, a simpler way, I think, to think of this is how many of you can turn on a dime? You know, if you're going fast, you got momentum. Can you stop all at once? Can you turn? Or does it take you a bit to stop and come back? Well, that's kind of what the chain's doing too. You can think of it both ways. In order to start falling, the falling chain yanks on this chain and pulls it up out of the cup. It has to come up first. And so it speeds up, stops, or slows down, stops, and then speeds back up. Just like tossing a ball up in the air. And so it takes a little bit. You know, it's got inertia. And so it rises up and then falls. Both can explain it. And you can understand both now. This will work with Mardi Gras beads too. It's kind of fun. Want to do it again? You just have to give me a minute. The only trick is you can't wad it up and throw it in or it'll get really tangled. So you kind of have to lay it in like this. I went to the store. It wasn't this beaker, but I took a cup that I wanted to use. And I did this off the roll. I just filled my cup up. Took it to the cashier, some service attendant, you know, said, "I'd like this much, please." He goes, "Well, how much was it?" "I don't know." So they got to measure it and charge me. There we are. Get in there. All right, ready? We'll watch the top here this time. Let it fall. Oh, that's a good one. All right. That's what I got on energy. Before we move to simple machines, let's ask you some clicker questions. Review and see how well this is sunk in. Oh, screens, that could help. All right, so there's your login info. The polling's open. You get set up and start answering. What are we doing? How you guys doing? Getting there? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, we made it to 50. Woo! I don't think we've been to 50 before. All right, most of you think A, the rest of you C. 400 joules, 1600 joules. The answer is 4,000. So, see, I got more work to do. This one, I purposely, I had not worked this problem yet. Wanted to see what you could do. We have a 200 kilogram crate. We'll come back to these, don't put it away. Just, let's work this one on the board. The mass is 200 kilograms, because kilograms is mass. It's hoisted 2 meters up. Exactly. And it took 4 seconds. All right, and I asked for work. How much work is done? You agree, it takes work to lift it? Well, we could do it that way. Work equals force times distance. How much force is required, minimum amount, to lift this thing up? 200 times 10? That's its weight. Yeah, you have to at least lift it with its weight upwards to counter its weight down, right? Minimum. So its weight is mass times acceleration. We'll use the acceleration due to gravity. 200 kilograms, 10 meters per second squared, 2,000 newtons. Okay, we know the force needed, minimum, to lift this thing up. It actually will take a little more than that to get it moving, but once you get it moving, you only need 2,000 to keep it moving, the rest of the 2 meters. So 2,000 newtons, and it went how far? 2 meters. And a newton meter is a joule. So it took 4,000 joules of work to lift that thing up. Yes?
So what are the seconds?
It's superfluous information to confuse folk. Well, this follow-up question uses the seconds. It's the same question, but they ask something different, and there you need the time. And we're going there. But it's true. Sometimes, though, you look at it and you think, wait, I don't know what to do. You just start looking through equations. Which one uses distance, time? And you start plugging and chugging, but you're not thinking. You're not processing. It takes work to lift it up. That means I have to apply a force for a certain amount of distance. How much force is needed? That's what we just did when you get at 4,000 joules. That's all we needed. There is another way to look at this, though. Some of you might have done it a different way. Once we do this work, what form of energy does it have? Right. Gravitational potential energy. If total energy is conserved and we just put 4,000 joules into it, it's going to have 4,000 joules when it gets there, because it's all potential energy at that point. So knowing that, or stating it, you could have found it this way. What's its mass? 200 kilograms. What's gravity? 10 meters per second squared. How high up is it? 2 meters. Can you see that's exactly what we did mathematically? This is the force. That's its weight, raised 2 meters. They both arrive at 4,000 joules. Energy is conserved. I just thought of a follow-up question. Let's say I drop it. It's at the top, not moving, and I drop it. How fast will it be moving right before it hits the ground? You don't have to tell me the value, but what would you do? I raise something up 2 meters and drop it. How fast will it be going right before it hits the ground? You raise something up just like this, 2 meters. You know it took 4,000 joules to get up there. It has 4,000 joules. You let go of it, whoosh, it falls. Right before it hits the ground, how fast is it moving? Kinetic energy is the key. Let's start there. How much kinetic energy will it have right before it hits the ground? 4,000 joules. Energy is conserved. Do you see that? Because that's the connection here. 4,000 joules kinetic energy right before it hits the ground. Kinetic energy is 1/2 mass times velocity squared, and that equals 4,000 joules. So the mass was 200 kilograms, right? Divide 4,000 by 200. 20. Multiply the 2, that'll be 40, and we square root that. I don't know, let's say it's 36, so it's about 6 meters per second, or you plug it into your calculator. So yeah, it's going to go about 6 meters per second, a little faster. I think that's cool. You can know how fast something's going just by how high up it was. So with this energy, there's multiple ways you can solve things, realizing total energy is always conserved. Does it make sense now? At least at the moment. I encourage you to rework this, rethink it on your own. The next question is, and you can't really see it, but it's how much power is required to do this same thing, to raise it up? 200 kilograms. Let you see it for a moment. So we just found how much energy was involved. Let me open it up. How much power then did that take to raise it up? 2 meters. Your clue is, you know it took 4,000 joules of energy, work to get it up there. Oh yeah, I wanted to see what you're doing, Patricia. See if I could get a clue why this isn't working while the others are thinking of their answers. See, what do you think? And I'll watch you enter. Actually, at this point, we can change your answer. Let's just pick something. And a check mark. See, that's good.
It's working now, because when I pushed the button last time it did that, it showed I picked
Okay,
A.
yeah, it should be good. You can choose a different one on top over that while it's still open. Because I just randomly guessed. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Hey, we're more consistent here. 1,000 watts. Yeah. Power is the rate we use energy. 4,000 joules expended in 4 seconds. So it's in the denominator. You divide, you get 1,000 watts. Joules per second. Very good. All right, go. Charging elephant has kinetic energy. So it must also have, you know, because you're smart now, it also must have what? If something has kinetic energy, it has to have something else. What is it? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Two more of you out there. Come on. Last chance. All right. Most of you think all of those. All right. Work is force times distance. Potential energy is mass times gravity times height. Momentum is mass times velocity. So if something has kinetic energy, a charging elephant, it's moving. The only thing for sure you know is that it's moving. It has a velocity. But if it's going flat on the ground, it's not changing its gravitational potential energy. It could, but we don't know that. If it's running uphill or anything. And we don't know what it's pushing on, or something's pushing on it. There's no work. Remember, objects can't possess work. They can do work on something. My point here is its momentum is the correct answer. Momentum is mass times velocity. If it's moving, it has to have momentum. It also has to have kinetic energy, because those are both dependent upon velocity. Does that make sense? That's all I was trying to get at with this question. All right, I'll ask you some more next time. We'll start off with that and move into projectile motion. I got a couple quick things about simple machines and let you go. So inclined planes we already discussed. That's a simple machine. Machines cannot multiply energy. They don't magically give you more energy. We often think, oh, I'm using a machine because it makes it easier. That's non-science talk. Well, what's easier? They require the same amount of energy because energy is conserved. By easy, we usually mean the force, like we discussed here. So a ramp can do that, but so can, here it is, a screw. A screw is another simple machine. It's essentially just an inclined plane wrapped around on itself, right? Drill bits use a screw function. Here's my little model. Here's a screw. You can think of those as the threads. Well, this is paper. If I unravel it, you see it's just a ramp. It's an inclined plane wrapped up on itself. So when you're trying to screw into something, it's just like you're going up a circular ramp. What does that do to the distance it covers? Increases the distance. If you increase the distance, then it can require less force for the same amount of work done. You could lift it straight up. You could try to punch it straight into a piece of wood, right? But that's nearly impossible to go that distance straight in. But if you go round and round and round, now we can do it. Takes less force. But you got to go a farther distance. Same amount of energy. That's how jacks work. Like this. This one's kind of fun. Assuming we can have a volunteer. Anybody want to sit on this for me real fast? Doesn't hurt. All right, thanks. Do you think I can lift him up?
Probably.
Let's see. No. All right, sit down. All right, now you have to balance, obviously, but
Okay.
let's see, am I going the right way? There we are. Come back here. You have to raise up so you twist with it.
Oh, okay.
You got,
There you go.
darn friction thing. I know, it's a balance issue. We'll just rotate you with it.
That'll work.
All right, help me out. Go with me. It'll still prove the point. So I can do this for a long time, right? Look, I can do it with my pinky here. With just one finger I'm pushing. And we can stop. You get the point. Thank you. And I'll just raise this up for emphasis. Look, I raised him that high, 2 inches. Ta-da! Not very impressive, but I could lift a whole car that way with my finger if I do it far enough. That's how jacks can work, at least screw jacks. Another type of simple machine is a wedge. Do you see how it's just kind of 2 inclines? It spreads it out for splitting things, or door stops. The last one I'll do is a lever. And then we'll cover some others next time. But levers are great. You've all heard of levers. So this lead brick is 26 pounds. It's pretty heavy on its own. Well, you can use a fulcrum. And I can have it way over here, and I can't lift it. Because I'm exerting a force, but I have to do it this far. This little. It's this ratio. If I'm over here, most of you know it's a lot easier. You know, you can do it with your pinky. I can lift it up. But notice which side moves further. This one. I'm using less force. I don't need the 26 pounds times whatever its weight is. But I have to go a farther distance. I'm still exerting the same amount of energy to do this as it takes to raise this like that. More force, shorter distance. Less force, bigger distance. So machines change the distance or the force, not the energy. There's 2 more, a wheel and an axle, and pulleys. I can hit those next lecture. See ya.